This concept was further the concept of the response spectra, which is a very nice tool for seismic design, and which is quite useful for a design office, because in the design office you cannot, it is not possible that for every problem you carry out a very detailed analysis. uh, so we have to have some handy tool, and response spectra is an approach towards that direction. And then after the initial proposition of the concept by Hausner, then it was further enriched by Newmark and Hall considerably, and then further many people has contributed for the development of the design response spectrum, which we are uh, using presently in the code. We'll talk about that in details. Now, before that, uh, I would like to just give you a bit of the preamble, like how we get the earthquake data measured. Earthquake data is measured by seismograph, which is the which normally has three parts. You are being able to show in this figure. What is happening is that, see, if there is an excitation in this direction, then this drum is rotating. Whenever the excitation starts, then the drum keeps on rotating with a particular angular speed. So this axis, these parallel lines, so if you proceed along these parallel lines, that denotes the time. And then this pendulum, that only moves because of the movement of the ground, and these are very rigid things. So these pendulums swing as the ground moves, and then depending on the swinging of the pendulum, here is a pen, so it makes the marks, and then the drum keeps on rotating with a particular speed. Therefore, we get a graph which gives us the idea about the acceleration versus time plot. So the major objective is recording of ground motion data, then the analysis of recorded data for monitoring of seismicity of a region, and then depending on the seismicity of a region, values of different seismic design coefficients are determined. So this we will discuss in due course. So do you understand this concept of the seismograph? This machine is called seismograph. So do you understand this? How this is happening? So this is a schematic diagram. Of course, now this machine has become much more complicated. It is automated, but the basic concept I am just trying to give you, that how the recording takes place. Well, then if we just look at a typical acceleration time history, say the kind of history will get recorded, that will be like this. So this is, in this direction, ground acceleration is expressed in terms of g. That means this is 0.1 means 0.1 g, 0.2 g, 0.3 g. So you see that this El Centro 1940 earthquake is a benchmark earthquake which is used for many analyses, and the highest peak ground acceleration was about 0.3 g on this side, and even on the other side, negative side also, the minus 0.3 g. So, and you are seeing that this motion is very sporadic. But then if you carry out the numerical integration, and then you go to the you try to draw the velocity versus time plot, then it looks like this. That means you see that it becomes relatively more smoothened because you have made an integration. If you integrate the acceleration time history, then you will get the velocity. And then Well, if you further integrate it, then you will get the displacement. And you see that the displacement, the acceleration data is very randomly varying. So very, very sporadic nature. But as compared to that, the displacement data is become of much smoother nature. So do you appreciate this? You understand what I am meaning? Uh, so, with this discussion, then we will try to go to the concept of response spectra. So, let us just try to think about the whole thing in a very simplified way. Let us consider just a one-story system, okay? And then all the masses we are considering, that is lumped at the roof level, and then these are the two columns, and this is the ground. Then the damping, which is offered by the atmosphere, as well as the internal damping of the structure system, because cracking takes place when vibration takes place. Small crack keeps on occurring. So there is some kind of energy dissipation or energy absorption, other way speaking, and so that also adds to the damping effect. So the total damping is expressed as a viscous damping. That means the damping which is proportional to the velocity, that already we have talked about. And then this is denoted by this damper, okay, the total damping which is acting. Now, when an earthquake comes, what happens that the ground immediately say this is the positive x direction in which we will measure the lateral movement. Now, when the earthquake suddenly comes, then the ground starts moving in the negative x direction with a value say ug double dot. Then what happened that because of the inertia, the heavy mass at the top, it try to return back its original configuration. Therefore, there is a relative displacement is created between the mass and the ground. And because of that, the deformation takes place. So that basically initiate the vibration, and then as long as the ground keeps on accelerating into and fro direction, then this vibration keeps on continuing. And then when the ground movement stops, then after some time, this undergoes free vibration, and then this free vibration uh, dies away, because that is the transient part, as we have discussed. And so this same system can be expressed as our classical system, and that's how the whole concept emerged, because Hausner, being a mechanical engineer, was dealing with this kind of a classical system. But then he say, oh, you see, when he started thinking about this building, then he realized that the same system can be idealized as like this, where the total stiffness, lateral stiffness of these columns, each column, if there are both end fixed, then it has a stiffness of 12 bi over L cube, all of you know. So depending on the number of columns, so if n is the number of columns, then n into 12 vi by I over L cube. So he says that, well, then this total stiffness can be represented by this spring K, and then the total damping can be represented by this damper, and then both of them are parallelly connected to the mass M. So he says that, well, so that means the mechanical engineer can work on this problem. And then the governing differential equation was written. And then if we draw the free body diagram, then if the positive movement, if the direction of the positive movement is this, in this direction, right hand side, then the restoring force, that means if the spring is extended, so it will try to pull back the mass m, and then the damper will also exert an opposing force against the movement, and then as the D'Alembert's force, the total acceleration of the mass is x double dot plus ug double dot. Okay, if you consider the total acceleration, the relative acceleration is x double dot, but the total acceleration, if we consider, then it will be the acceleration of the relative acceleration of the mass plus the acceleration of the ground, and therefore it becomes x double dot plus ug double dot. So the D'Alembert's force, or the pseudo force, which we apply, that will be equal to m into x double dot plus ug double dot. And then once we apply this force, that means we convert the system into an equivalent static system. So now we can consider that the system is in static equilibrium, and considering that, we can write down the equations: m into x double dot plus ug double dot plus cx dot plus kx equal to 0. So just, dividing both sides by m, we can rewrite it in this form: x double dot plus c over m x dot plus k over m x equal to minus ug double dot. So then, the point is that this ug double dot is not a harmonic function, is not, in fact, it is so sporadic that it is very difficult to be expressed through any mathematical function. If at all it can be expressed, then it has to be expressed by a Fourier series. So that will be a very complicated form. So the only way to solve this differential equation is by using numerical methods. No analytical method will be possible for a real earthquake to be applied, because you know that if the function is not a harmonic function or an exponential function, it is very difficult to get the solution of the differential equation for this type of second order differential equation. And not only that, even if the function would have been on polynomial or any other type, then also we would not have been able to find out the solution. And here in the real situation, forget about the polynomial. In fact, there will be no function. It will be only can be numerically described. That means the time versus acceleration at a regular interval of time, say in an interval of 0.02 second, which is normally taken as the interval in all the accelerographs. So that means at an interval of 0.02 second, what is the value of the acceleration? So we get a t versus ground acceleration history, and with that set of data, we have to solve this differential equation numerically, and that becomes, and then from this numerical solution, if we can try to find out the value of the x max, that means during the history of this vibration, what is the maximum displacement has taken place. If we multiply that displacement with the stiffness of the structures, that means K, then we will get that how much force, how much maximum force is occurring, or maximum shear is occurring in these columns, and then from that we can calculate the bending moment in the column, and then we'll be able to design the column for that bending moment. So that is the philosophy. That means our objective is to get the maximum displacement, truly speaking, from the design point of view. Rather, we have less interest about the entire variation of the displacement as a function of time. So that will be of less use. And realizing that, then people thought that, well, can we really have some handy curves so which can give us the maximum displacement or maximum response? So the people started thinking in these directions. And then you try to notice this equation. You see that zeta is the damping ratio and omega is the natural frequency. These two are the features of the system. On the other hand, minus UG double dot, that is the external disturbance or perturbation which is applied. So, you know that if you are walking, if somebody just suddenly comes and try to hits you, so you will also react, and then both of you will fight, and the result will depend on how powerful relatively both of you are. Similarly, here there is a system, and then somebody is that ground acceleration starts creating some disturbance. Therefore, the resultant vibration that will be a negotiating that will have a negotiating effect between these system parameters and the external disturbance. So it will depend on both. I mean, the system parameters will participate in the form of zeta and omega, and the external force will participate in the form of the ground acceleration. And then if we can have a plot of, say, x max for a different value of omega, or otherwise speaking different value of lateral period t, and if we can produce some handy curves, then possibly we'll be able to get x max, or otherwise speaking the maximum response. Now so that was the attempt which was made. So people just try to make to write program, and then these following the numerical methods, they try to have a plot where they are having the plot of the maximum acceleration as a function of time for a different value of zeta. For example, I'm showing here zeta equal to 0.0, that is the undamped situation, which is of course hypothetical. Then if the damping increases, then the response curve will go down. So 0.02 is normally for the steel structure, and 0.05 is for the concrete structure. 2% and 5% of the critical damping. And this acceleration is called spectral acceleration because it is the maximum acceleration. That means over a spectrum means a large horizon. So over a large horizon, we are just picking up the maximum value. So that is why it is being called as spectral acceleration, or we can plot it for velocity. We can plot the maximum value of the velocity, and we can also plot it for the maximum value of the displacement. And accordingly, we will call it acceleration spectrum or displacement spectrum, blah, blah, blah. So this is X max, and this X max could have also written as SD, that means spectral displacement. The spectral means the maximum. Okay, over a horizon, we are over a large spectra, we are picking up the maximum value. So it is chosen over a large horizon. So from that implication, it is denoted by SA or SD or SV, something like that, all the response quantity. So these kind of plots are called response spectrum. That means the response spectrum can be defined as a set of curves plotting the maximum value of response quantity, and this response quantity may be displacement, may be velocity, or may be acceleration as a function of frequency or period for various value of damping ratio. Now, say if we try to plot the displacement spectrum, then how will it look like? You see, that this is tried for a given earthquake data. So this data is the ground acceleration. Okay, a real ground acceleration. Then that means, you see, when it is 0.5 second, the system is having a period 0.5 second. That means, you see, that if this tick denotes the stiffness, then its stiffness will be 3I by over L cube. So these ticks will be very less, as for the small value of the period t, this will be less. For a larger value of period t, this will be larger. For a further larger value, this will be larger. And you realize that the stiffness 3I by L cube, as this stick will be larger, so the 3I by L cube, that means this, the stiffness of the system will be lower as the period will be larger, and therefore they will more, that means a more flexible system. Larger period means a more flexible system, and a more flexible system will undergo larger displacement, and that is reflected. You see that if we plot the displacement, then it comes like this. You see, it comes like this, and then at various points. Okay, so if we plot it as a function of time, then you see at this point, that means for a stiffer system, the variation is very small and the displacement is also small. So if it is slightly larger, 1 second, then there is a little bit more variation, and Umax becomes a little bit larger. Similarly, for 2 seconds it becomes larger. For 3 seconds it becomes considerably larger. So that way, if we then take the maximum of these values, and then if we plot it, then we will get a curve like this. Of course, there will be sporadicity, that means ups and downs, because it is of random nature. But the overall trend is that with the increase in period, the displacement will increase. So this will be the nature of the displacement spectrum. We have just, we are showing it for a typical case of zeta equal to 0.02. So for 0.05, the curves will be further lower, okay, because more damping means less response. So, this is an introduction about what the response spectrum is, and then we will continue the discussion further in the next class. Now, over this discussion, if you have any question, you may please feel free to ask.